Let's suppose you're given this triangle problem. You have a triangle, side length 6, 3, and 4. You would like to know all of the angles. So I think the way I'm going to proceed is I'll do alpha, and then I'll leave beta and gamma for you all to do as halves of the room. And then we'll come together and see if the answers look reasonable. So let's suppose you want to find this angle alpha. You want to find that angle alpha. The law of cosine says that the square of the side opposite alpha is equal to the sum of the squares of those two other sides minus this defect. So let's use that. So the law of cosine says that 4 squared equals 6 squared plus 3 squared minus 2 times 6 times 3 times the cosine of alpha. Sounds like something that could be solved for cosine of alpha? Probably. I'm going to go slightly out of order. Let's see what this equation says if we do the same thing centered at beta. What's the side length opposite beta? 6. So if we wanted to think about cosine of beta, we would say 6 squared is equal to the sum of the squares of the remaining two sides minus 2 times the product of those two sides times the cosine of beta. And yeah, I have enough colors. I can do this color coding in a reasonable way. What if I try to do the same thing at gamma? What equation would I write down then? Yeah.
3 squared is equal to 4 squared plus 6 squared minus 2 times 4 times 6 times the cosine of gamma.
Nice. Groovy. So, I think I'll talk through alpha. Those who feel like they're very confident should just start walking on one of the remaining two, because then I'll split you all up. And then I'll split you all up, and you'll solve the remaining two. So let's try to solve this equation for cosine of alpha first. What's the first thing you would want to do if you wanted to solve that pink equation? Maybe start by simplifying. What's 4 squared? What's 6 squared plus 3 squared? I hear a 45. Does that agree? Yeah, I think it does. Minus 2 times 6 times 3 is 46. And then there's a cosine of alpha. So step 1, simplify the things you can simplify. So how many people think they would be likely in the next step, if this were like a high pressure situation, would you be to rewrite this as, let's see, 45 minus 36 is 9, right? How many people would be likely to do that? But it's like obviously the wrong thing to do, right? Multiplication is resolved before subtraction. So you should think of those two things as being grouped together. So that's a wrong thing, but it's a wrong thing that I want to emphasize because that's like a super common mistake I see on exams. And it makes me sad whenever I see it. And it's better for you if you don't make me sad while I'm grading. Anyway, so solve that for cosine of alpha. What seems like a good next step? Say that louder. Subtract that 45. Gosh, 16 minus 45 is negative 29, I think. Nice. All right. What next? Yeah. Divide by negative 46. Negative 29 over negative 36 is equal to cosine of alpha. All right, what next?
Did you get that decimal approximation?
You could. I won't yet, because I'm not at the final answer. If you take a premature decimal approximation, you are propagating around in errors. So, say louder. Take the inverse cosine of both sides. I'm going to do one other thing. Negative divided by a negative becomes positive. Maybe you did that automatically, so it wasn't worth saying. Cosine inverse of 29 over 36 is apparently equal to alpha. And let's do this first. 29 over 36. Is that like a number that you see on the unit circle? No. So it's not something you can just evaluate without resolving to a machine. So let's resolve to a machine. What's the inverse cosine of 29 over 36? I guess I could do that too. I don't need that right now.
About 36.34 degrees.
I think that sounds right.
Is it okay that I'm in degrees?
Does the problem say whether you should be in degree or radian mode?
No.
So as long as your answer is clear, I'm happy. Should we be in degree mode or radian mode? Like just personal preference. Degrees? Radians. All right. If you want to be in radians, go for it. Well, I guess I can write down both. So what was the approximation in degrees?
About 36.34 degrees.
36.34 degrees. And we also got it in radians. What is this about in radians? 0.63 radians. Groovy. Folks feel pretty good? So, here is what I would like you to do now. Find the angle beta. Find the angle gamma. And I don't know, do you think it'll be like an extremely similar amount of walk? I bet. You get to the point of having progress or even just a full-blown answer that you want to compare with other people around you, go ahead and compare them. We'll compare them all together soon. You seem impatient these days. Igor, excited.
Your patient works just out.
Igor. Shall we come together? What is the angle of beta? About 117.27. I like you are going to the same precision as above. Be consistent. What was the exact value? Yeah. Inverse cosine of negative 11 over 24. Did I hear you right? Awesome. What was it in radians? As long as we're doing both. 2.04 radians. Nice. Folks feeling pretty good? And are any different values for beta? Let's go ahead and just remark on one thing. The thing inside of the inverse cosine turned out to be negative. And maybe you'd get upset with that because these are like supposed to be ratios of side lengths. They're like side lengths, and then you do a bunch of algebra to them. So it makes sense that negatives can appear. And in fact, the range of inverse cosine is quadrant 1 and quadrant 2. Which of those two quadrants has cosine negative? Quadrant 2. So that angle beta, should it be obtuse or acute? Do the numbers say it's obtuse? Nice. Yeah, slightly bigger than pi over 2, or slightly bigger than 90 degrees. All right. How about gamma? Yeah.
I got inverse cosine of 43 over 48, or about 26.38 degrees. I did not get anything in radians.
26.38, you said?
Yes.
Cool. Anyone get it in radians?
0.46 radians.
0.46 radians. Nice. All right. So, the last homework I want to make here is a checksum you can make to build confidence in your answers. What do angles in a triangle have to add up to? 180 degrees. All pi radians if you use radians. Let's add these up and see what we get. And these are decimal approximations, so I wouldn't be surprised if the hundredths place is off. In fact, I kind of hope it is, just to like demonstrate that it can be. So let's see. Let's add these angles up. So 46.34 plus 117.27 plus 26.38. So how many people think they'd be likely to just bust out a calculator to compute this sum of numbers? I guess that's fine, but like you do also know how the addition algorithm works, right? Okay. Yeah. Oh, you want to actually see what I write? Yeah, that makes sense. I just written down the three numbers with plus signs between.
It does equal exactly 180.
That's fine. It wouldn't had to have. It would have been perfectly fine if you rounded up with 180.01 or something. Each of those numbers, maybe two of them rounded up, one of them rounded down, in which case the whole result would have been screwed up. Let's do the same check in radians. So, 0.63 radians plus 2.04 radians plus 0.46 radians. I'll do the addition this time because it's fewer digits. 13 carry the 1, 11 carry the 1, 3.13. Is that pretty close to being pi? Yeah. And in this case, it is off by that last digit, but that's just fine because I expect the error to be about that big. Groovy. Maybe I'll make one last comment as like a WebWalk hacky thing. So let's suppose you're doing a WebWalk problem. You're solving one of these triangle problems. And you find out that like everything's right except one of your angles is incorrect. And it tells you which of your inputs is incorrect usually, right? Not all the time, but most of them. Do you think you could just like figure out the correct value for that wrong angle if you know that all the other ones are right? Yeah, great, do that. Cool. Any questions about law of cosines right now? People feel like the computations they just did went pretty well?
I just had one question.
Yeah.
On E for like the inverse cosine, I had initially had like, I'm just not sure how you got like negative 11, because I had like 36 being equal to like 25, and then minus 24 times the cosine of theta, but I must have done something wrong.
Yeah, so tell me this, that thing you just said. Tell me what you had there.
So I set it up like, so I did like 36 is equal to 25,
Mm-hmm.
and then minus 24 times the cosine of theta.
Mm-hmm.
And then, well, after that, I subtracted 25 from each side, but that
Cool.
would be positive 11, not negative 11.
And you have to get rid of the negative 24.
Oh, yeah.
Yeah, so that negative will move, you lost that negative in your process.
Okay.
And because that's easy to accidentally do, so there's that one negative sign, it's worthwhile doing this checksum where you see if the angles actually add up to 180 degrees. Cool. And I guess the other thing to think about is, so in this angle, this problem, so this triangle is obviously not drawn to scale. That side length 6 is like pretty long compared to the other two sides. It's really close to just being the sum of the other two sides, which is the biggest it could possibly be. So you expect that angle beta to be like pretty big. And without that negative sign, I think you wind up with like, did you wind up without the negative sign inside of the parentheses?
I had like a value that was really close to that. Well, but like I don't know, I just like calculated it again, and it wouldn't have been like, because I took the inverse cosine of 11 over negative 24, and I got that same result
Without the negative sign?
without the negative sign.
Shouldn't have. You should have gotten 180 degrees minus that.
Well, no, I had negative 24 as opposed to negative.
Oh, you did have the negative. It was just in the denominator.
Yeah.
Oh, yeah. Then you're fine. You're fine. You should simplify it. Then the negative sign should come out of the denominator.
Yeah.
Yeah. Yeah, so if you, without that, you would get like 60 degrees-ish, I guess, which is smaller than you would expect this angle to be. Neato. Folks feel good? Let's do some applications. And like, more proper-looking applications, not like, here's a triangle, find the side lengths, like, applications with units and stuff. So, there's no subtlety in the units. The units are also consistent, so you also like, don't need to be careful to convolve. Here's one. While walking in the woods with Robert Frost, you come to a fork in the road. Robert Frost takes the path less traveled by, which makes all the difference. You, on the other hand, look at the path less traveled by and the path more traveled by and say, well, that path looks way more well made. There's a reason it's more traveled. So you take that way. These paths diverge at 45 degrees. Yes. Because you're walking on a better maintained path, you can maintain a significantly better clip. It's really more pleasant. You travel at a speed of 4 miles per hour while across the cave. If you walk for 1 hour, what is the distance between? And I can say more if you want, but my intent is like to pause here. Do people have an idea of how to begin on this plot? Does anyone want me to do something like draw a picture? I'll draw a picture. So let's draw a picture. It's not going to be a very detailed picture, but I think it'll be good enough. So you're walking together, you and Robert Frost. You come to this fork in the road, and these paths diverge. I'm not going to try to draw this to the correct scale. That doesn't look like a 45-degree angle. That looks like a 90-degree angle. I guess I already said 45 degrees. But what's the angle between these two paths? And you keep walking for a while. After 1 hour, how far have you walked?
4 miles.
4 miles. Why 4 miles?
Because you walk 4 miles per hour.
Awesome. 4 miles per hour times 1 hour is 4 miles. How far has Robert Frost walked? 3 miles. And what's the thing you want to find in this question? Distance between. So that would be like, what's the length of the line between those two rightmost dots? So it looks like, here's the length I want to find. We should give it some sort of variable name, right? What should we call that distance? Awesome. D for distance. Also reasonable would have been C because that's what we called side lengths, or X because it's an unknown. I don't know. All right. So let's look at that triangle. I see a triangle now. Do I know 3 facts about that triangle? That means I should be able to figure out all of the facts about that triangle using some combination of law of sines and law of cosines. Should I use law of sines or law of cosines?
Law of cosines.
Law of cosines looks useful. Maybe I'll give you, like, you have like that lookup flowchart. But maybe I'll suggest this instead. The law of sines works really well if you have information about a thing and the thing opposite. If you look at that triangle, do you know an angle and a side opposite? No. The known things are all lumped together. So law of sines isn't what you want. What does the law of cosine say in this situation?
B squared equals 3 squared plus 4 squared minus 2 times 3 times 4 times the cosine 45 degrees.
Nice. And you want to solve that for D, I guess. So the actual bit of algebra is trivial. Take the square root of both sides. But then I think there's a fair amount of simplification. So tell me what you get. The equal sign doesn't look enough like an equal sign. D equals and is approximately. Let's see what we get. Well, I think I'll have enough time to get started with this. I'll do one of these. Oh, sorry. So once you have an exact value and maybe a decimal approximation, maybe compare with those around you. You're allowed to do that. This isn't a test. Cool. So what are people getting?
About 1.31 miles.
Do I hear different answers?
Yeah. I got 2.83 miles.
Do I hear other answers? And I think the second one was the more popular one. So let's write out both of the exact values. Let's try to track down where the inconsistency is. What's the exact value for this distance? That's still an approximation. Because you said 8.203?
Yes, for 8.2.
So since that 0.03 isn't exact either, though, is it? So what is the exact thing that's under the square root? Yeah.
25 minus 2 cosine 45 degrees.
I buy that. I would say it's not totally simplified, though. What's the cosine of 45 degrees? Root 2 over 2. So here's the quick heuristic if you don't keep the unit circle with you at all times. In the unit circle, just in quadrant 1, there are 3 interesting angles. 40 degrees, 45 degrees, 60 degrees. So you only need to remember 3 numbers. The 3 numbers are 1/2 root 3 over 2 and root 2 over 2, right? Since that's 45 degrees, that's the one in the middle of 1/2 root 3 over 2 and root 2 over 2. Which one of those is the middleist? Root 2 over 2, because 2 is between 1 and 3. So, this is equal to, after you simplify, the square root of 25 minus 24 root 2, but then you divide by 2. So I guess that's 12 root 2. And there are some bits of algebra that let you break that up into a sum of 2 square roots, but I think that's good enough for now.
Oh, I see where I made my mistake.
Awesome. And then I guess that if you actually ask a machine to compute that now, it's about 2.8. Is that a 3 or a 7? 2.83. And the units are miles. Folks feel pretty okay about this application? Yeah. So trigonometry is important because it lets you translate distances plus some angle information to other distances. And if you want to compute the distance between two things, that's important. And there are loads more good applications, like in the textbook under the section, if you go to the exercises. There are lots of cute, but still applicable things. Let's do one other thing like this. So you travel 30 miles due east. You then turn 30 degrees to the north and travel 1 mile forward. How far are you from your starting location? Well, I guess I don't know, alternately, maybe you're like a golfer or something dumb like that. You want to golf, but there's a lake in the way, and the lake you can't hit directly over or something. Or maybe you do want to hit directly over. And you know some pathing information. You know that there's some path that goes 3 miles and then 1 mile. Golfers hit balls 5 miles, right? That's about a normal golf stroke? Yeah, I think that's right. So totally reasonable for a golf example. Let's try to figure out how far you would need to hit this ball to make it to this, I don't know, there's like a little flag and a hole in the ground. That's how you golf, right? I've gone golfing once, and it was a league game, and I didn't finish any of the holes. It was like a 12-stroke maximum, I didn't finish any of them. Then afterwards, I went to the bar for drinks with the person I went with, and they just made fun of me, and then gave me a box of golf balls. It was really unpleasant. Anyway, that doesn't matter. Do you think you could figure out the length of that missing side in this triangle? And as with any of these diagram questions, just start by finding things you can find. So in this diagram, what looks like something you could determine? Yeah.
Angle C.
Yeah, the angle, which I guess you want to call C. How big is that angle? 150 degrees. Oh, cool. So, now ask yourself, what is useful, law of sines or law of cosines? Law of cosines looks reasonable. Determine that missing side length. Right here on 3.9-ish. That agree? In fact, I stalled for long enough saying that just rambling that I guess it's not surprising that people probably had this minutes ago. What are the units?
Miles.
So there's the approximate value. Does that agree with what other people are getting? What's the exact value? Cool. Maybe I'll pause for a moment. Does that agree with what other people are getting? Should I talk through any of the actual computation? People feel okay about it? Nice. Yeah, so if you have information about how to get to a point, you can determine the honest-to-God distance to that point using these law of sines, law of cosines tools. And before I start in on this next packet, because we'll make some headway in it, I want to advertise that there's a ton of extra credit in this packet. So even on this next page, all right, so we wrote down this formula that is the law of cosines. I didn't give you any reason to believe that it's true. The reason it's true isn't deep. You can break any triangle into two right triangles by like dropping in, I guess usually they're called altitudes. If you do that, you drop this little altitude and study those two right triangles. If you do enough, you can get this side length C in terms of the other side lengths. And this page guides you through that. Complete this page, talk me through what you get, that's an extra credit. On the next page, you can use this to compute some novel things. For instance, this little wedge shape in a circle is called a segment. Do you think you could determine the area of that? Find a formula for the area of a segment in a circle. You can probably find a formula for a regular n-gon. If you have a perfectly symmetric shape, which has some number of side lengths, they're all the same length, you can determine the area of that thing in terms of, I guess, some angles. Finally, there's yet another area formula, which is a super classical one that doesn't get talked about in this class, just mainly for time reasons. If you know all three sides of a triangle, do you know that triangle? Yeah. As we've seen, you can use the law of cosines and determine all the angles. If you know all the sides and all the angles, then surely you can figure out the area. In fact, we have an area formula that's like 1/2 AB sine theta. So you should be able to put those two things together and get a formula for the area of this triangle in terms of the side lengths. Do the work to get it. The algebra gets a little hard. Not that hard. Maybe there's not enough space on this page to do this one. But to help you out, to see if you have it right, I've given you the right answer at the bottom. So figure that out, and then come talk through it with me. You know, people think they might be tempted by any of those extra credits? Nice. Let's start it on what is the final note packet that we'll use. So this is it. This is the last note packet. I have given you a total of apparently 196 pages over the course of this semester. So this packet is all about some trigonometric identities that we'll build this weekend. And let's start by just picking on that one identity. What does that mean? And to figure that out, let's just ask this. What does the Pythagorean identity say? Sine squared plus cosine squared equals 1. Squared is technically correct. But 1 squared is 1, so I'll leave that last square out. It says that sine squared of any angle plus the cosine squared of any that same angle is always equal to 1, and this is true for every angle theta. So no matter what angle you plug into that equation is always true. So this isn't an equation you could solve for theta, because it's just an equation that's always true. That's what an identity is. An identity is an equation that's true no matter what input you plug into it, as long as you don't fall outside of some domains. But there's no domain issue here, so there's no domain issue. And we've seen some of those in the past. Let's maybe even write down one that doesn't have to do with trigonometry at all. What's the log of A times B? Log A plus log B. How many people just remember that? How many people think it would probably be a good idea to have that on note sheets, at least for that final exam? I guess logarithms aren't in the content for what we're doing right now, but they will appear definitely on the final. Equals log A plus log B. That's another example of an identity. That's an equation that's true for every choice of A and B, as long as you don't accidentally land outside of the domain. Which can happen, right? Like, if A and B are both negative, you're in the domain on the left-hand side, but not the right. So it's still an identity, even though it's false from a domain. Cool. So we've seen lots of identities in the past. In fact, here are some other ones we know. What's tangent equal to in terms of sine and cosine? Sine over cosine. So one of the identities we know is tangent theta is equal to sine theta over cosine theta. What's cotangent equal to? Cosine theta over sine theta. Secant? One over cosine theta. If you said sine, you can be forgiven, but like, that is incorrect. Secant is 1 over cosine. I know it's weird because there's no co in secant. If you want the real reason that those are named the way they are, there's an extra credit that was a while ago called something like the other trig functions, in which you do a bunch of geometry and figure out what these trig functions really are in terms of some diagram. Cosecant. What should cosecant be? 1 over sine, the only other thing that's left on the list. So those are identities. Those are equations that are true for absolutely every choice of theta, as long as you don't accidentally land outside of the relevant domains. There's the even-odd identities. Cosine of negative theta is the same as... I said that with a question mark at the end there. So it's definitely either plus or minus cosine theta, just from context, right? Folks for plus cosine theta? Folks for minus cosine theta? Folks who would like to be reminded of the easy way to figure it out? Nice. In terms of the unit circle, what is cosine? X. So I'll start at an angle of 0. I'll rotate up, because that's what positive angles mean. I'll rotate down, and I'll try to do so by like the same size angle. How do the x coordinates differ? They don't. They're the same. So cosine doesn't care if you rotate up or rotate down. And that's an identity. That's something that is true for absolutely every choice of theta. Same thing for sine. Sine of negative theta is negative sine theta. And you said that with more confidence. Sine is odd. How about tangent of negative theta? That is correct. It is negative tangent theta. And we're given space here because this is an identity we can derive in terms of other identities. What's tangent in terms of sine and cosine? So tangent of negative theta is the same as the sine of negative theta divided by the cosine of negative theta. Oh, cool. Do I already know what the sine of negative theta is? What is it? What's the denominator? Just cosine theta. Is that negative the tangent of theta? Excellent. So I've even spaced it out correctly. So you can build new identities from old. I guess the other way of seeing that is, in terms of the unit circle, tangent is like a slope. So if you start at an angle of 0 and rotate up and rotate down, I see two different lines. How do their slopes compare? They're additive opposites of each other. So, neat. Adding pi over 2. What's the cosine of theta plus pi over 2? So even if you don't remember this, do people remember knowing this? Okay. We did cover it. So let's maybe even draw the picture that gives you this result. So, and maybe before doing that, how many people in fact know what it is? What is the cosine of negative theta? We know what's the cosine of theta plus pi over 2? Say louder.
Negative sign?
I hear a negative sign by looking up in the notes.
Yeah.
Okay, let's see how to just remember that without looking up in the notes. How big an angle is pi? 90 degrees. Pi over 2. You answered the question I asked instead of the one I should have asked. Pi over 2. How big an angle is pi over 2? 90 degrees. And so a right angle. So if you want pi over 2, go a right angle and then go an extra bit of theta. So if you compare, there's an angle of theta. There's an angle of pi over 2 plus theta. It looks like this x-coordinate is negative. But it's negative the same as the y value is positive of the plus 1. So it should be negative the old y value, so negative sine theta. What about the sine of, what should sine of theta plus pi over 2 be? That's just cosine theta. Because, and this picture tells you it, the y value of theta plus pi over 2 is positive, which is the same as the x value of the original angle. Neato. So, I wanted to get to like the angle addition formulas, but I'm not so upset that I didn't right now. We'll start with those next time. If you really want to know the angle addition formulas now, you're very impatient. It's super easy to find them. Look them up anywhere. The textbook, for example.
I don't use a lot of water now, because I'm fasting.
I just have a quick question.
And I want to go to use.
So like if
Yeah, you need to give these people that. You need to go through these and eventually you know what the whole is.
yeah.
Like you need to figure out how to plug this information into that.
Did you see how detailed my planner? Yeah, I would die. But the one thing about it, well, like, my middle school used to sell planners, or like, you would get your and then you like had to use it, and so, yeah, so now that I'm like, not required, I'm like, I have to do it.